Cool. Let's get started. We're very excited to have Rose Yu from UCSD to speak with us today. And Rose is an associate professor at the Department of Computer Science and Engineering. She earned her PhD in computer science at USC in 2017, and she was subsequently a postdoc fellow at Caltech. And her research focuses on advancing machine learning techniques for large-scale spatial temporal data analysis with applications to sustainability, health, and physical sciences. And a particular emphasis of our research is on physics-guided AI, which aims to integrate first principles with data-driven models. She's a recipient of the Presidential Early Career Award, PCASE, the highest honor given by the White House to early career scientists. Double Young Faculty Award, Army ECASE Award, NSF Career Award, Hellman Fellow, Faculty Research Award from JP Morgan, Facebook, Google, Amazon, and Adobe. Several Best Paper Awards, Best Dissertation Award at USC, and she was also named as MIT 35 under Technology Review Innovators under 35 in AI and Samsung AI Researcher of the Year in 2025. So I'm very much looking forward to the talk. Rose, please get started.
Okay, thank you so much for the introduction. And today I want to share some of the recent work from our group on grounding foundation models for physical sciences. So I direct the spatial temporal machine learning lab, where the goal of our group is to advance machine learning for large-scale spatial temporal decision-making. So there's a lot of excitement around foundation models. What I mean by foundation models is this family of model that can solve a variety of tasks. So before, when we wanted to solve tasks like text-to-text translation or text-to-image translation, we would have to build different models for each of the tasks. But with the rise of foundation models, we do not need to build separate models for these tasks. Rather, we have a unified foundation model that can solve all of them together. This is the recent Stanford 2025 AI Index report, where it shows the performance relative to human baselines. So the vertical dashed line in blue is the human performance. And each solid line here represents the performance of a particular benchmark over time from 2012 to 2024. As you can see, the performance of these benchmarks rises really quickly in the past few years, including multitask language understanding, reading comprehension, and even PhD level science questions. Some of these benchmark performances are closer or even surpassing human baselines. Despite the success, there's also failure modes. So in December 2024, OpenAI released Sora. It's a video to text to video generation model. And here, if we ask the model to generate a sport telecasting of a gymnastic performing aerial flip during a floor routine, this is what the model generates. And clearly, the videos, despite OpenAI's claim to learn the physics of the world, it still generates rather bizarre videos that's not physically consistent. Another example for foundation models is in this paper called Easy Problems that LLMs get wrong. So if you ask GPT-4 which weighs more, a pound of water or 3 pounds of air, then the model will say 2 pounds of bricks with more than 3 pounds of air. Another example is if you ask Class 3, I get out of the top floor, which is third floor at the street level, how many stories is a building above the ground? So after a long chain of reasoning, the model will still say the building has a total of 3 stories above the ground. So these examples highlight that existing foundation models still lack a framework of physical reasoning. They do not understand the sense of numerical relationships and the sense of spatial reasoning. Despite the fact that there's a lot of improvement for these foundation models and the performance of this model is changing really rapidly, there's no guarantee that they can generate physically meaningful answers. So the research that our group has been pursuing in the past few years is called physics-guided deep learning, where we wanted to address this fundamental challenge for AI in physical sciences. As we know, deep learning and physics have rather complementary strengths. So in deep learning, we have very expressive models and they're very efficient to compute. They can generalize well to unseen scenarios, but they often lack a framework of physical reasoning. They're black box models that are very difficult to interpret and require a lot of data to train. So typically for training our reinforcement learning algorithms, we will need millions, if not billions of trajectories. This is definitely infeasible for physical applications where collecting data is highly expensive. And from a physics perspective, a rather more general in scientific field, there's a rich domain knowledge that we could leverage, and we built models that are very easy to interpret. These models can learn with only a few data points, but the downside of these models is they're very rigid. They rely on very strong assumptions about the underlying system, and they can be expensive to compute at high resolution. And they don't generalize well, meaning that if we need to model a system with different initial and boundary condition, then we'd have to design a different type of model. So in these two communities, we have these different tools. In machine learning, we use neural nets and graph networks to model statistical patterns of the data. In scientific fields like physics, we have differential equations and the concept of symmetry that can be used to model space and time patterns. The goal of physics-guided AI is trying to bridge the best of two worlds together so that we can imbue trustworthiness in the field of AI and science. So I wrote a survey paper with my student. It was published in PNAS 2024, where I have described this overarching framework of physics-guided deep learning, and I encourage you to check it out. In this survey paper, we categorize different methods into these four paradigms. So when you have strong physical knowledge on the left, then you will use methods like residual modeling or trainable operators. But if you have very weak inductive biases about the data or the task that you want to predict, then we will use weaker models, weaker inductive bias models, such as equivariant learning and disentangled representation. So this figure is actually from UChicago data science, where I really like. The idea is if you look at the entire scientific discovery pipeline from collecting observations to asking the right question to generate a hypothesis, and then performing experiments to test the hypotheses, and furthermore to analyze the data from experiments and draw conclusions. At every step of scientific discovery process, AI can be very helpful. And in fact, in my group, we have developed tools to assist and accelerate every single step of scientific exploration process. But for today's talk, I will focus on a few components. For example, we have derived models that address the problem of generalization. The idea is if we want to build digital twins of complex fluids, then we will typically use a deep learning model to predict the future evolution of velocity field. But the challenge is if we do not have a physical law built into the model, then when the test data are shifted away from the training set, the model will have a hard time generalize to new dynamics. We have bring the ideas of symmetry from physics to deep learning, where we embed the symmetry constraints into the architectures of neural networks. And then with that, our model can perform much more robustly when the test data scales further and further away from the training set. Compared to ResNet, which is a video prediction model, as we shift the test data further away from the train set, then these predictions will get much worse due to distribution shift. Whereas if the model is aware of the symmetry in the data, then it will have very robust performance. We can build symmetry also in the latent space of the system. We have developed the deep learning models that can emulate complex fluid dynamics like this. More importantly, if we have the system that changes the system, the condition, for example, F equals 9 means there's a buoyancy force, which is a driving force that disturbs the system. If we change this buoyancy force from 9 to 21, then the baseline muscle would completely fail due to distribution shift. But because the symmetry encoded in the model our method diet is still able to predict very accurate small-scale dynamics. We also contributed to the field of epidemic modeling. So we worked with CDC during the years of COVID to develop fast surrogate models that can accelerate simulations of multi-agent compartment models for disease modeling. So in this case, we designed a neural process model that can capture the uncertainty of the underlying dynamics. What's important here is instead of training the model from a given set of data, we used a Bayesian active learning scheme to iteratively query the simulator and incrementally update the data, update the model. Compared to offline training methods, our Bayesian active learning paradigm can reduce the data sample complexity by 68%. And more importantly, our prediction from the deep learning model closely mimic the ground truth. So in the bottom here, you're looking at the predicted infectious number for asymptomatic and symptomatic cases. And the red one is the ground truth from physics-based simulator. And the blue one is a prediction from our surrogate model. The predictions from our model not only mimic the mean prediction quite well, but also the confidence intervals, showing the importance of uncertainty. And because of the surrogate model is much more efficient to do inference compared to physics-based simulators, we can shorten the simulation time from 1 week to 1 hour. We participated in the national COVID-19 forecasting team with another 40 or so national teams. This is a competition, or rather a cohort of teams that trying to forecast the next 4 weeks of death cases for COVID-19. Among 40 also national teams, the team that I led was ranked #1 nationally for forecasting uncertainty, precisely due to the fact that we have this hybrid model that incorporate physics and deep learning. We also work with people that works in drug design. So in this case, we will integrate physics-based binding free energy calculation with a generative model. So a lot of generative models have been applied to generate small molecules, but a lot of the common drawback is these small molecules are not chemically valid or physically consistent. So by integrating these binding free energy based calculations into generative model, we can then reverse optimize in the latent space to design a molecule that is much faster, but also more meaningful. And this is the small molecule that we have developed through our generative model with desirable properties, including log P QED score, which is drug likeness score, synthesizability, and binding affinity. And interestingly, when we look at the compounds suggested by our model, it has better binding affinity than tamoxifen and raloxifene, these are the drugs on the market. We further developed methods that can integrate different fidelities of simulations, from very cheap molecular docking-based simulator to very expensive molecular dynamics-based binding free energy calculation. We treat this hierarchy of simulations as a set of oracles and design a Bayesian active learning scheme to iteratively query individual oracle and then integrate the oracle response into the generative model. Our generative model is a multi-fidelity generative neural nets, and then it can be guided by this hierarchy of oracle signals. So this work was recently appeared at ICML, and now is the state of the art for generating small compounds with desirable chemical properties. So today's talk is about foundation models. The example that I showed you before is how we have developed the physics-guided deep learning and successfully applied them to a variety range of applications. But then when we think about grounding, right, we have to look at the literatures available for grounding foundation models. Typically, people will use things like RLHF, reinforcement learning with human feedback, to ground the foundation models, or RAG, which is to retrieve external resources as vector embeddings, and then imbue the model with additional knowledge. There's techniques about grounded supervision, which is to use paired data, label data to further fine-tune the model for a particular task. And then there's also joint embedding like CLIP, where you can train pairwise embeddings for different modality of data. So the idea of grounding is trying to imbue a sense of trustworthiness or finding a model for a particular set of applications using external information. But when we think about grounding for physical sciences, a lot of the techniques will break down. For example, if we think about RLHF, that would mean we need to constantly ask our domain expert in physical science for their feedback, which is very expensive. And for REV, we know it's very brittle and not stable. We don't have very rich label data in physical sciences, unfortunately, so grounded supervision is also not feasible. And when it comes to joint embedding, basically we have massive amount of numerical data in physical sciences, but then the paired data of rich text and numerical simulation are almost non-existent. We don't have the equivalent of CLIP for physical science. So the way we think about grounding foundation models is to leverage the fact there's a lot of rich numerical models in the form of differential equations and simulations. So we will then use deep surrogate model that we have already built to use them as an oracle or a verifier, and then these signals will come back to our foundation model. Using these fast emulators, we can query the universe or physical universe as the world model, and then these signals will then come back to our large language model to ground these models with scientific knowledge. And fundamentally, when we do this type of grounding with simulators or emulators, we can imbue a sense of trustworthiness in physical science. So first I will talk about how we can build very fast emulators for foundation models like diffusion models. An example we try to show is probabilistic forecasting. So for diffusion models, there is this paradigm called Gaussian-based denoising, where you basically iteratively add Gaussian noise at every step of the sampling process. And then when we revert the process, we can then reconstruct data from noise. So the classic diffusion paradigm based on DDIM and DDPM iteratively add Gaussian noise to the data. But for forecasting dynamics, which is in the examples here, it basically ignored underlying temporal dependencies in the data, and therefore lead to very slow sampling for high-dimensional videos. We propose diffusion, which is the data-driven segregation scheme. Rather than adding Gaussian noise, we train a separate neural network, which we call temporal interpolator. This temporal interpolator will then couple the diffusion step with the time step in dynamical system, significantly reduces the computational complexity with respect to memory footprint, data efficiency, and the number of diffusion steps. By coupling this temporal interpolator with a forecasted network, we can capture long-range dependencies and generate probabilistic ensemble forecasts. This animation shows how diffusion iteratively performs interpolation and forecasting. And we save the intermediate steps of diffusion as forecast and use this intermediate forecast to further refine our diffusion sampling process. We can show that diffusion is implicitly modeling the solution to an ODE, where the interpolator and forecaster is corresponding exactly to the solution of the underlying ODE system. But the classic DDIM paradigm actually models a different type of dynamics, which also explains why it is slower compared to diffusion for modeling dynamical systems. We showed examples of diffusion compared with a set of baselines. The visualization shown above is the ground truth, the baseline dropout, multicolor dropout, and the diffusion model. The bottom one is the quantitative results for our method compared to a wide range of baselines for sea surface temperature forecasting and forecasting Navier-Stokes equations. The metrics we use include the probabilistic metrics like CRPS and SSR, as well as deterministic metrics and MSE. We also reported the runtime for generating the samples. So MCVD is a video diffusion baseline that was developed by OpenAI. Compared to MCVD, ours has very comparable sample performances, but we are 20 times faster than typical video-based diffusion models. We further extended this work to model the global climate, and in this case, we need to account for the 3D spherical geometry of the Earth especially the distortion in the polar area. And therefore, we replaced the backbone in the original diffusion model from a U-net to a spherical neural operator. So using this functional representation of the velocity of the vector field, we can then capture the three-dimensional spherical geometry of the Earth. And then the sampling process is the same as the diffusion model, where we couple the temporal interpolator at the forward pass and then use the forecaster to generate samples iteratively. This paper got the Best Paper Award at the ICML Machine Learning for Earth System Modeling workshop. Compared to physics-based simulators shown on the left, this is a sample from a global climate model. Spherical diffusion, our model, can generate quite realistic velocity emulations for a different range of variables. So this is the wind speed variable, and you can see that the model captures the small-scale dynamics quite well and the turbulent patterns in the underlying system. And then this model is actually much faster than physics-based model. It can shorten the runtime from 6 months, which is a typical time used for model run, to about a week. So we also recently moved towards the paradigm of agentic AI for physical sciences. Grounding foundation models means we can then also couple these foundation models with a variety of tools available to our scientists. So then the system will orchestrate the different type of tools using the reasoning ability of these foundation models. Again, for physical sciences, there are a lot of unique challenges. For example, the tools that we have are typically numerical simulators and that are based on coupled differential equations. They're very, very expensive to use. The most common tool used for agents is things like web browsing, which is nowhere comparable to the cost needed for running expensive simulators. We also have formal reasoning ability, like formal tools, formal methods available as verifiers for physical sciences. And then most importantly, we also have a lot of uncertainty, both in the tools themselves and then the agentic environment that the system needs to execute in. So how do we integrate different type of uncertainty in the system is another challenge. So for the rest of the talk, I will talk a little bit about the new work that we have developed along this line for agentic AI. And in particular, I'll show you how we could use these adaptive ways to use tools and reduce costs, and then also integrate formal methods tools as verifiers for solving questions in physical and mathematical sciences. As mentioned before, we have very expensive tools in physical sciences. Despite the fact we can develop fast surrogate models like diffusion that shorten the time from 6 months to 1 week, still running one tool that takes 1 week is not a trivial amount of effort. So we need systems that can adapt based on the difficulty of the task. This paper was published in ICML, which we call grounding, adapting while learning with adaptive tool using. Typically, when we think about an agent, they have a bunch of tools, include memory and literature. And then, we have a set of planning that allows the agent to plan for the future actions. So in this case, you think the tools of physical science of these numerical simulators. So the first step we need to figure out is how do we allow these large language module agents to talk to the numerical simulators? So by interfacing scientific simulation, we basically designed a set of templates such that we can fill in the numbers in the template and then allow the large language models to understand the abilities of these simulators in natural language. So for instance, we can ask how much will the temperature in Gigorogo in 2018 under particular scenario blank change if the emission of carbon dioxide is decreased by some parameters blank. So then the scenario and parameters are essentially templated questions that we could ask and then query the simulator to get the corresponding response. We can also ask open-ended questions. For example, design a maritime route from Singapore to Dubai that increases the sulfur level by a certain amount blank, then the route. the proposal should have the least amount of impact under a certain scenario blank. So then these type of blanks are filled in with numerical input, and then we will then instantiate the simulator to generate labeled examples. After we generate a large number of labeled examples with our simulator, we can then fine-tune our model to learn the difficulty of different type of problems. So there are two stages in this agentic framework. One is we call the word knowledge learning, which essentially just means supervised fine-tuning. So we will supervise fine-tune these models with the label data we have generated before, such that we can allow the agents to know about the knowledge in the simulator. And the next phase is tool usage adaptation, which means we will decide the difficulty of the task. If a task is very easy, and we will try not to use the tools because of its cost. Instead, we'll try to answer these questions from the agent internal memory. Only when the task is very difficult, then the model will start using the tools. So we can train this model to be adaptive using the tool using traces. This is the kind of effect where we have this kind of adaptivity. So originally, the blue one is the easy problem and the red one is a hard problem. So there's a lot of hard problems to the model for this foundation model if we do not fine-tune the model with the simulator knowledge. But once we have word knowledge learning, where we injected knowledge from the simulator to the agents, then what was the hard problems before are no longer difficult. They become easy. So we can see that the vertical boundary pushed to the left. And with tool use adaptation, we can now see the model will try to use tools only when the problem is hard. But then when with easy problems, it will try to use its internal memory and reason about the answer. So with this kind of adaptive framework, we can show that on a variety of physical scientific problems, like physical simulators for Mujuko, partial differential equation solving, or answer questions in climate and epidemiology, thanks to our paradigm, our model was able to outperform the frontier models by large margin. I want to draw your attention to these two methods of our own, which is tool using that is always forcing the model to use tools in yellow, and our adaptive framework. So some people might say, if you have tools available, why don't we just have a model to always use the tool if cost is not a concern? And then my counter argument is that sometimes if we always allow the model to use tools, this agent will become over-reliant on the tool usage and instead become less generalizable to unseen tasks. So that shows the effect of having this type of adaptability in using tool and choose to use tool based on the difficulty of the task.
Can I ask a question?
Sure.
Yeah, so maybe I missed this from earlier part, but do you mind explaining like what are these tasks? What are the questions looking like in these? And then how did you collect those kind of questions?
Yeah, it was showing this here, right? So I mentioned these are the examples for them, how much for climate, we can say how much temperature will change under a particular scenario. We can ask the agent to design a shipping route from Singapore to Dubai. And then these will be the questions that we ask the agent.
I guess
And we generate again?
yeah, sorry. I guess the question will be, are these questions from real data or like it's is it constructed from real scenarios or is it more like synthetic?
So it's constructed based on our simulator, right? We have
I
these
see.
numerical simulators that is used by our scientists to model real world patterns.
I see. Thank you.
Okay, next I want to talk about how we can utilize a lot of the formal reasoning abilities in physical science to improve the agentic performances. As you know that in the world of mathematics theorem proving, there's a lot of models out there, including those what we call the informal reasoning models, like Cloud GPT-5 and Gemini. And recently there's a news about Gemini with DeepSync officially achieves the gold medal standard in International Mathematical Olympiad. So despite these models are very performant in solving mathematical proofs, the issue is that these informal reasoning models, they often hallucinate. So the proofs that they generate still need to be manually checked in order to see, okay, whether the proof is correct or wrong. So this verification process is very time consuming and error prone. And then there's no guarantee that these output or these theorem proofs by the model are in fact 100% accurate. So then because of that, for mathematical proofs, there's a wide range of tools called the theorem prover, right? So there's a set of tools like Lean, Isabella, or Rock that are programming language tools designed to generate formal proofs that can be then verified programmatically. So then because of this formal verification tools, we have these prover LLM, like DeepSeek prover or the Godot prover. So these LLMs are specialized LLMs that are designed to generate proofs in formal language rather than informal natural language. The benefit of this type of foolproof LLM is that the output can be programmatically verified, and then there's no hallucination. So the interesting thing about these two classes of method is that for informal reasoning model, they have very strong performance, but the output is not programmatically verifiable. On the other hand, the prover LLM can generate formal proofs, but the overall performance is still inferior to informal reasoning models. So the paper that we recently published at NeurIPS 2005, actually to appear in NeurIPS soon, is trying to bridge this gap of between formal reasoning and informal reasoning. We proposed this system called Hilbert. It's an iterative solver that utilizes the informal reasoning ability of frontier models with the formal proof generation skills of these LLM provers. So given the target theorem, Hilbert will attempt a formal proof generation with a prover, which is an LLM prover, a formal LLM prover. Upon failure, it will decompose the problem into sub-goals and then try to solve these sub-goals with prover, followed by a reasoner. A reasoner itself is an informal LLM. If both strategies fail, it will resort to recursively decomposition until all sub-goals are resolved. And the picture in the bottom is this important step of sub-goal decomposition. So we have a retriever, which is essentially equivalent to the RAG system. So it will retrieve a lot of useful lemmas for completing a proof. And we have a reasoner, which is an informal LLM that can understand the semantic meaning of a mathematical theorem and decompose that into smaller problems. It will generate a proof sketch for the formal verifiers to verify. And the verifier we use here is Lean. So you can see that through this kind of iterative process, the iterative recursively break down a difficult mathematical theorem into easier sub-goals and then intertwine these informal LLM formal reasoning models with formal verifier who can start to solving a lot more challenging problems, but also still guarantee the output proof is in formal language. Hilbert is right now the state-of-the-art theorem prover on a lot of the benchmarks. So if you work in this area, there is a benchmark called Mini F2F. The blue bar is highlighted is our method Hilbert. So it combines informal reasoning with formal LLMs. And then you can see that if we combine Gemini with Godot prover, we can have 20% improvement over the existing Godot prover. And similarly for DeepSeek, we can have 35% improvement for any mini F2F. Another benchmark is called the Putnam bench. So the Putnam exam is those high school, close to college level math competition. And it's very difficult. As you can see, the Godot prover, which was the best prover out there, open sourced, only have 13% accuracy. And C prover is from ByteDance, but unfortunately, we cannot verify the numbers because the code is not open sourced. Hilbert, our model, improves over Godot prover from 13% to 70%. And this is the leaderboard that is shown public. It's benchmarking formal mathematical reasoning, and our method Hilbert is #1 in the benchmark. Finally, I wanted to talk about this new agentic framework that we have built to integrate a lot of tools that I developed before, including surrogate models, adapting while learning, and then thermal verification into a holistic framework for solving climate science-related questions. So this is a project that I led by DAPA, funded by DAPA, called Genie. And the idea is we wanted to consolidate wide range of knowledge, including numerical simulations and text information like research articles and textbooks, and build a foundation model to solve a variety of tasks in climate science, including forecasting, causal inference, and scenario creation. And what's important, we need to ground these models with physical laws in the form of simulators and surrogate models, prediction uncertainty, and in-context learning. So we have this new work called Zephyrus. It's an agentic framework for weather science. And given a query, this LLM-based agent, Zephyrus, will write a code block, which is then sent to the code execution server. The server orchestrates several tools to execute the code block and returns the execution result to the agent. The agent then decides either to execute more code or refine its output or responds back to the user. So there's a set of tools that are very specialized to weather science. WeatherBench 2 is a benchmark dataset released by Google. GCP Simulator is our collaboration with Google to develop a JAX-based simulator for global climate modeling. Forecaster is a SOTA method for forecasting based on Stormer, and Geolocator is a customized tool that we have developed that can map a geographic location to a numerical latitude longitude values on the Earth. We have two contributions in this paper. One is the Zephyrus world, which is an agentic environment so the agent can execute tools in parallel. And then the Zephyr bench, which is a set of benchmarks that we have created. It's a semi-synthetic task that we created. Essentially, we take a weather text corpus that we have curated, and then we will use an extraction agent to extract the simple verifiable claims. Then we will use LLMs to generate reusable templates based on these claims, and we will have human experts to verify these templates. So rather than having humans verify individual examples, which is very expensive, we just have our experts verify the templates. And using the template, we can then run our coding agent to generate code that solve problems in this template, and then we can then synthesize a lot of these templates and code together to generate benchmark data set. So in this benchmark, we have in total 31 tasks. For each task, we have 2,000 examples per task. We did the initial benchmark for a lot of the frontier models like GPT-5 and Gemini and GPT-OSS. The highlight here is we want to compare with the non-agentic foundation model, which is a text-only LLM. So with our agentic framework using Reflect, which is a reflective reasoning paradigm like React, and then direct is directly answered without reflective and retrial, right? So the both agentic framework can outperform the text-only LLMs by a large margin, which is expected because these text-only LLM can only answer questions from internet knowledge without having access to this wide range of tools. Finally, I just wanted to highlight this video demo that we have where the idea is we can have users interact with this foundation model in natural language. And then basically you can include a weather data, say WeatherBench 2, start a timestamp and a location, and you can ask a question like plot a linear regression of average temperature surface area in Japan in 1970-2020. And the model will start generating code and execute the code in an agentic environment. So then you can see now the model produce a response in the plot and also the numerical answers for the Japan surface temperature and the linear trend. You can also examine the code that have generated to understand what the model is doing and then potentially figure out any bugs. You can also model to generate a meteorological report for a particular region. So this digital Earth that we have is fully interactive. And then the model will use the forecaster tool to generate a report for this region, including both rich text and numerical information. You can ask the forecasting questions to generate the future forecast. And you can see that for each of these questions, it will be a separate task in the past. Then we would have designed different models to solve each of these tasks, whether it's forecasting or report generation or running simulations. But now with the rise of foundation models, we can just have a unified model in a single system that we can ask all these questions in natural language. So this has significantly reduced the effort of model building and lowered the access barrier for climate domain knowledge. Okay, to summarize, I believe that I have showed a lot of examples in our group at the intersection of AI and physical science and math and physics. So I believe that computing and AI are transforming our scientific discovery process. Science represents an exciting frontier for AI, and AI represents the most exhilarating new instruments in the hand of scientists. We imagine a future where our scientists and AI agents can work side by side, from hypothesis generation to experimental design to data analysis. AI will co-pilot with scientists at every stage of scientific process. Scientists will provide necessary guidance to ensure AI is conforming to the scientific truth. Okay, so here is the references and the code are available on my website. You can also follow our group's work via social media, and also wanted to thank the funding agencies for supporting this work. Thank you.
Any questions?
I have a quite general question. I
Sure.
saw you have many great works that range from a diverse range of areas like physics, climate, epidemic, and mathematics proofs. Like, how do you quickly get into an area and gain insight from this area?
Okay. That's an interesting question. So, because I think as a computer scientist, we're trying to keep thinking in more abstract fashion, right? We work on more abstract methodologies, and then we apply these methodologies to concrete applications. So one is because of our training, we're used to thinking in more abstract terms. Then the other thing is I have been very fortunate to have a very collaborative team and have very strong collaborators in all these different areas, from climate science, epidemiology, math proving. We always have experts in that field who are open to collaborate with people from AI, and they also have their own unique domain knowledge that they can bring into the team. Lastly, I guess I have been very lucky that my students are very strong. Like most of the effort are just led by my PhD student and postdocs. So they forge new passes in the lab, and in my group, I always encourage people to explore new directions, and I'm glad some of them worked out.
Thank you.
Okay.
I guess I think from your point of view, what do you think is the main bottleneck for the final vision to be realized, like scientists having AI as co-pilot? Or like, do you think what would be the main roadblock for that to happen?
Yeah, I think that's an excellent question. Like the Genie demo that we showed is only touching the surface, right? We're seeing that on the benchmark we have right now, even the frontier model with our agentic environment can only achieve 50 to 60% accuracy. That just means the current agent, they can understand like common sense questions, but for very hard scientific questions, they still don't have the specialized knowledge. So one of the gap is how do we inject this specialized knowledge into the model? So we're also thinking about like fine-tune the model, and then with these domain-specific verifiers, right, potentially increase the general reasoning ability of these models. But while also we need to be careful about catastrophic forgetting, so that the model will not lose general reasoning abilities. The other challenge I would say is for some physical sciences, let's say drug design, right, we have always been limited by the experimental capabilities. As a faculty in computer science, we're used to do things in computers, despite the fact that our model can generate extremely binding, favorable compounds in silico. There is a big gap between what works in computer and what works in practice, because for chemical process and biological process, there's a lot of unknowns. So the compounds still need to be tested and synthesized and tested in a real world environment. And that is a very, very long road ahead. And I think if we want to have AI scientists that can complete the loop, right, then we need to have high throughput experimental facility to support that. And then we can then bridge the gap between digital world and the physical world.
Yeah, thank you for the great talk. I think it appears to me that there's the works you showed about these agentic frameworks show that the agents can already use the tools pretty effectively, given some questions. And it appears to me that since there's still a gap between, say, like you are given as a domain scientist, you were given a hard research question, or like you're starting a new research project, and how do you arrive from that to more specific questions that you want to use the tools to address? It still seems a little bit unclear. So I guess have you thought about that, and what would be a good approach?
Sorry, I don't think I understand the question. Can you maybe elaborate?
Yeah, so for example, with the questions you presented, it's like with the climate science question, it was something like predicting sea surface temperature, or something like that, which can already use some computational tools to get. So the agent will be able to, I guess, direct these tools to get answers. But I guess on a higher level, if say a climate scientist is trying to solve the harder research question of how does sea surface temperature affect, I don't know, I'm not an expert, how does sea surface temperature affect like regional precipitations or something? It seems to me that that part isn't quite connected with where you use the AI agents to call the tools and then perform some computations. So
like if you're asking about how, if the question is like how the sea surface temperature related like carbon emission, right? That's a causal inference task. So like if you wanted to solve a causal inference task, then you will use causal discovery tools. And in fact, in my group, we have developed several work that's specifically about causal discovery, causal representation learning. So that could be a separate tool, right? I guess maybe if I reframe your question a little bit, like if a scientist have a very concrete question, right, that is formulated precisely, then as long as there is existing tool that can solve that question, then I think it's not a difficult task. I guess the difficult part is the scientists come in, they don't have a concrete question in mind. It's more exploratory, right? So then there is no clearly defined tools available or tasks to be solved, and it's just exploratory, then I think that is a different type of research question. But that's not the goal of this agent, I guess.
I see. And is there anything special? I guess you mentioned some like fine tuning about the reasoning capabilities of the agents. I guess I didn't quite get that part. Like, how did you in the later half of the talk of these agentic frameworks, did you do any fine tuning to make sure that the orchestrator agent actually performs well in terms of selecting which tool to use, or How,
Oh yeah,
how
like so the mass proving agent is completely inference time. There's
Okay.
no fine tuning involved, and just with that, we already had number one in the Putnam bench, like
I see.
70% compared with previously 15% accuracy. The Genie agent, we have fine tuning currently in implementation, but not in this paper. Like the benchmark result I showed is only just about inference time. That's why, you know, the performance is only around 50% for our benchmark. And I do believe that fine-tuning the model to know how to use these tools, right, integrating this idea of adapting while learning based on the difficulty of the task, and then choose which tool to use and how to use them is very important. And then I believe that would boost the performance by a lot. So that's something that we're working on right now.
I see. Sounds good. Thank you.
Sure.
Great. I think if there are no more questions, let's all thank Rose again. And thank you
Okay.
so much for taking the time. And
And you take care.
talk.
Bye. I'll
Bye.
see you in San Diego. Bye.
And